So, first up, hydrogenation. All right. What should I put here? I don't know. I'll just leave it like that. Okay. So for this one, you don't have to memorize the mechanism, but does anyone remember how it goes? Like, what do I need to do for hydrogenation? All right, so our first one is hydrogenation. So what are the reagents for hydrogenation? Well, we got hydrogen gas, right? But what else do we need to put in there? Heat? Yeah, we could put heat. What else? Well, heat, you usually don't need it. Alkenes are so activated, you don't really need heat. If it was if you're trying to break a carbon-oxygen bond, yes, you would need heat. But usually hydrogen, and what else do we need to get it to go? Usually a catalyst, right? So palladium on carbon, platinum on carbon, or platinum oxide. Those two work. All right, so the product here, we're going to get hydrogen, right, being added to both sides of the double bond. So what we're going to have here is hydrogen. So let's do maybe this one, pointing upward. Okay. Hydrogen. So they're both adding to the same side. But what other product do we get too? Is there any other kind of product we can get? So let's make this bond dashed. Okay, and we'll make one of these hydrogens dashed too. I forgot. All right, is one of these a stereocenter? Well, actually, I don't think they are they? So that's the only product we should get, right? Because do we have any stereocenters in here? No. Now, if I made one of these propyl group, then yes, we will have at least one stereocenter. So you can technically get the other and the enantiomer. Okay? So if you have a stereocenter, you can get the other and enantiomer as well. All right, what else has syn addition? So we have hydrogenation. All right. Well, none of the ones that have a radical or carbocation intermediate, those do not proceed by any syn or anti-addition exclusively. So the only ones we have here are this one. So let's talk about where two atoms add first. So there's this one, and what's the other one we learned? It has boron. Does anyone remember that one? Yeah, so let's just abbreviate it. Hydroboration / oxidation. Okay, so here, someone asked about the mechanism. Yes, you should know at least the first step of the mechanism. The second step, I'm not too worried about. The first one is more important to me, okay? The syn addition. All right, so this mechanism, we don't have to worry about it, so mechanism not required. But just know the metal is what binds them. Remember I showed you those pictures? We drew those pictures too. Just remember the metal acts as kind of like the enzyme, and everything gets absorbed, and that's why it adds to the same phase. Now, hydroboration oxidation, on the other hand, this first step, right, we have BH3, and it's like THF. All right, so what's the product of this first step? What happens to the alkene here? Hello. All right, so guys, think about what happens here. Is it anti-addition to the double bond or syn? Syn. Why is it syn? Why is it syn? Do you remember why it's syn? All right, hold on. Let me just pass back a few things here. Guys, think about how would this look like in a syn addition? Think about that. Just draw one enantiomer, stereoisomer, and think about how it looks as a syn addition. Yep. Final review out here. Okay. And it has all the answers, so you can use this. Huh? Yeah, one. Yeah. Use this stuff. All right. So, what's the stereo relationship between the hydrogen that's added and the boron group? So the H added and the BH2, are they going to be on the same side or the opposite side? Same side. So let's just draw the boron coming from the top face. And because boron is a little bit bulky like a methyl group, which side does it like to attach? The least hindered side. So we're going to put this, well, I think they're both equally hindered, right? Are they? Okay, sorry guys, let's make one of these an H. Okay, I forgot that if you put two substituents on there, they're both equally substituted, so you don't get a preference. Sorry about that. Okay, so the boron is going to go over here. And the H is also going to go on over here, okay? And remember, in BH3, which atom is more electronegative? All right, I think it might be hard to kind of think about that. Okay. Fonkel risk. I don't know, is it hydrogen? All right. What's more electronegative, boron or hydrogen? I think it's hydrogen, right? Slightly. All right, let me just remember that acronym. Does anyone remember the acronym for electronegative? Fonkel brisk. Okay. All right, so we look at our electronegativities. So just jot this down. Hydrogen is slightly more electronegative than boron by like 0.1. Okay, so hydrogen here, partially negative. Boron partially positive. Okay, and that's because boron doesn't have an octet, so it doesn't like those electrons. So it's not really electronegative. All right, so hydrogen here, 2.1. The boron is about 2.0. Oh, sorry, not 2.1. My bad. 2.2. All right, so slightly higher there. All right. So that's syn addition at the same side of the one. Does anyone want me to go over the mechanism? So, okay, sure. So let's go over the mechanism. All right. So what I like to draw is I draw this in brackets, and as the alkene is approaching here, right? So you're going to have, let's see, we're going to draw an H here, draw an ethyl group here. Okay. So what's happening here is that the boron is approaching. You're having two of its hydrogens fan out towards the less substituted carbon. So that allows it to be stable enough to approach. And then this hydrogen is small enough that this bond is going to form a partial bond to the alkene, partially broken there. And then what happens here is that the hydrogen bond will be attracted to the kind of more partially positive side of the alkene that we saw. Markovnikov selectivity and so forth. And then this alkene bond will form a bond to boron, and that's how you get the same face addition of this alkene. Okay, so I'm not going to mention what kind of selectivity it is yet, just so we kind of put them in separate categories. So this is the second syn addition reaction. And then what happens in the second step, the oxidation step? So hydrogen peroxide is used as an oxidant. You need to activate it. So you can activate peroxide by using acid and heating it. That's why store-bought peroxide is stored in acid, because it's very stable. It won't go off. Because if you add base, it decomposes and it produces oxygen. So here we're going to cause it to be reactive, decompose, okay, form hydrogen peroxide, and that attacks the boron, and you get alkyl migration, okay? But don't worry about that mechanism, okay? Not that. I'm not going to make you reproduce that, okay? Times 3 times like that? No. All right, but what's the transformation here? We get still the same relationship. So when the R group migrates, it's actually not doing an SN2 type reaction. It's actually just changing from the oxygen to the carbon now. So for this reaction, we get what replaces the boron? The alcohol, OH group, right? So the result of this step is the OH group replacing the BH2 group, and then everything else here stays pretty much the same. But what's the other possibility here? Do we only get one stereoisomer? Or do we get a mixture of something? You get an enantiomer. So you want to write plus ENT. Okay? So the result of this reaction, of both reactions really, syn addition. So let's draw the H's here. Syn addition. So both atoms here have the wedge notation here. All right? Just like these hydrogens are added to the same phase. So that's syn addition. Okay, so I think that's the only two where the double bond is breaking and forming 2 additional bonds. Did I miss any other syn addition? Well, I'm not talking about the other ones yet, the single atom. I'm just talking about like the 2 atom addition. All right, let's see. Use my handy sheet here. I think so. Oh wait, we're forgetting one more. So instead of forming just 1 alcohol, what about 2 alcohols? Isn't there a syn reaction for that one? Yeah, so let's put that as reaction B, reaction A. Okay, so there's another one that involves a certain metal here. So we're going to do syn dihydroxylation. Does anyone remember what this one does? So we take an alkene, and then what do we add to it? Say again? 2 alcohols, yes. So we're going to form a diol. Okay? Oh yeah, guys, don't forget nomenclature. 1 regular one, alkanes, 1 alcohol, or ether, and then maybe 1 alkene. All right? And don't forget stereochemistry, RSEZ. I highlighted that in that packet too, so if you want to review that, that's like a quick way to do that, quick guide. All right, so let's take cyclooctene, and we're going to react it with osmium tetroxide. So you might see osmium like this, and you might see a few like 2% H2O2 / something called MDO. don't worry about what this is. That's a catalyst. All right. So in recent years, osmium is very toxic and it's so expensive that we can't use it in molar amounts. So we have to add a catalyst so that this is now this is catalytic. Okay. So you might see that, but just remember it's osmium that's doing the chemistry. Hydrogen peroxide or this other oxidant, it's just a co-reagent to regenerate the osmium over time. Okay, so, well, osmium tetroxide looks like this. So what happened? What's the mechanism look like? I know it's a kind of funky one. These latter mechanisms we saw, they're kind of out there. They have no kind of trend to them, right? So what happens here? It sends hydroxylation, so both of these oxygens somehow must be adding to which phase? The same phase or different phases? Same side, right? Good. So this is a reaction. This is a mechanism. It's one we haven't really heard before. It's called cycloaddition. You're adding atoms, and the arrow movement looks like it's going in a Ferris wheel, so it's cyclic. That's called cycloaddition. All right, you form a ring by adding some atoms. All right, so what happens here is that one atom goes here, goes back to osmium, and then this bond right here goes to the alkene. And remember, we could think of alkenes. So I did put some resin structure type questions on there in the packet. In terms of resonance, you should know conceptually what resonance is. Whether or not you have to draw resin structures, I don't know. Okay? I would say I'm leaning towards don't worry about it too much. All right? Because we've seen it a lot. But if you need a refresher on resonance and why we do it, I put some examples in that handout. Okay, so we could always draw, so this is a very bad one, but you could kind of think like this, right? Your alkene is negatively charged and positively charged. Well, okay. Then I can use the electrons from oxygen to attack which side of my alkene? The positive side, right? So even when we draw this resin structure, it's still kind of valid for the reactivity. That's why we do them. We draw the resin structure. So you can kind of think of it like that. Negative charge attracted to one of the oxygen atoms. I push those electrons to osmium, and then those electrons from the other oxygens are pushed towards the other end of the alkene that's positively charged. And that's how I get my intermediate. All right, so this is kind of like example. Just say, oh, I could just draw this resin structure. All right, so the intermediate now. Let's draw our stop sign again. All right, so it's going to look like this. Okay, and then what's the second step here? So, okay. All right. Well, in terms of mechanism, don't worry about this step. You don't have to worry about the mechanism for this one. I don't think I even showed it to you. I might have, but it's not clear what it is. So what happens here? So I think the reagent, you need a reducing agent. You need to free up the oxygen. So you need to reduce those bonds somehow to free up the O bond. So I don't know, which reducing agent did we go over? Let's see. Was it DMS? Yeah, so it's either sodium bisulfite or you just use the smelly compound, DMS, which is another way to say CH3, SCH3. All right, so these sulfur compounds, they love oxygen, osmium. They'll just displace both of those oxygen atoms, and after workup, you will get your diol. All right, so you get, well, this diol is not stereocenter, so you don't have to worry about stereoisomers here. But if you did have a stereocenter, you would have to also write what? Well, it's an enantiomer, okay? So say I put like a methyl group on the right side or something, then you'll put an enantiomer. All right, so that's syn dihydroxylation. I believe that's all the syn ones for 2-atom addition. All right, are any questions on the mechanism? So this thing, okay, how do I add these bonds through the osmium? So just think about charge attraction. In this case, you can remember, you can draw a resonance form where oxygen now doesn't have electrons, so it's sort of partially positive. So that osmium kind of helps you, makes the tug of war for electrons not so even. So oxygen now is playing tug of war with the other oxygens, so it could be still partially positive. Okay, so we could still kind of label this partially positive too for the oxygen, even though that's kind of weird. And when you put a metal in there, things get kind of weird there. Okay.
So we don't need to reproduce the mechanism for the final though? We just...
Yeah, so I would say this. Study the mechanisms you're confident in, okay? If you know those, I'm more interested in what you know rather than everyone do this, okay? So there's some mechanism here you're like, okay, I don't remember this. Just look for a reaction. I might actually say, okay, just draw a mechanism for any reaction you just saw on the previous page or something like that. So you should know a variety of mechanisms. Don't just study alkene ones, because what if I ask you, okay, on this previous page, you did a bunch of reactions. Write the complete accurate mechanism for one of them. Okay, so you have opportunities to get points in multiple, what you know. But I would say this, for this one, I wouldn't worry too much about it. Okay? All right. Hopefully that was clear and I didn't get too much away. Okay, any other questions about syn dihydroxylation? So this is a great way to form diols just very easily from an alkene. It's not very easy to do unless you have an epoxide. Okay. So what other syn reactions did we have? Oh yeah, so I should also mention that there's another way to do this. I think it was presented in the homework. You can use KMnO4, potassium permanganate. It has to be cold, and it has to be at a very high pH. Okay, so sodium hydroxide. As long as you do it in basic conditions and cold, you can get the same product, but it's kind of overly reactive, so it's not very useful in synthesis. But you can do it if you control it. Okay. All right. Okay. All right. I noticed my handout here didn't even go over to the other reactions we saw. So 2 more syn reactions. Let's do the first one. What's the one with oxygen? We just add an oxygen atom. No, not that one. That cleaves the double bond. I just mean adding an oxygen atom to both of those carbon atoms. I think people also mentioned they want to go over this too. The reactions of a three-membered oxygen ring. What is that called? Epoxides. Epoxidation. All right. So what does epoxidation do? All right. This mechanism, don't worry about it. If someone chooses this mechanism, I'll be impressed. Just because it's very involved. And if you were to choose what mechanism you can do, I wouldn't expect anyone to pick that one. Let alone ozonolysis, which I told you don't even need to remember that one. There's tricks to kind of figure out what happens. Ozone. Well, we'll get to the ozone. All right. So what's the common reagents here we talked about? There's one you should have picked up on, MCPBA. And this is usually in DCM. This is just a solvent. So let's go over first what happens mechanistically. Okay. So the alkene lines up here. All right. So what I like to do is I kind of draw the H there. Oh, here. And here's just my R group. That's the rest of NCPBA. Okay. So what happens here? I think it's very similar to the osmium one. You're attacking oxygen again. But which oxygen do I attack in the molecule? Close. Not that one. So let's think of this structure right here. Sorry, it's all right. It's tough. All right, so remember this oxygen, right? This has a resonance structure where you have that. So my oxygen here is actually negatively charged. This one can be partially positive. What's going to happen to these electrons in the nearby oxygen if it's close to a positive charge? It's going to be pulled towards that, right? So my electrons here are being pulled this way by resonance. So I have a partially positive charge right here. So the last oxygen with the OH is the electrophilic position. That's your electrophile. All right, so now let's draw these arrows. Let me erase this. Okay. Let's redraw that. Okay. All right, let's see. All right, always forget. Boom. Okay, then one of these lone pairs goes down this way. Okay, this picks up this and this. Oh wait, I think I remember now. Sorry. Let's restart that. Okay, so this one goes over here. Okay. And then this causes these lone pairs to go over here. And then this goes over there. So the cyclic transition state there. And what happens there is now you're going to form an epoxide like so. And then this one's going to be staying in the back. So let's keep that in the back. Keep this hydrogen on the front. Okay, and then what you get at the end of this is the byproduct of the oxidant, and that's going to be an carboxylic acid, like that. Okay. So this mechanism, don't worry too much about epoxidation. Just know the end result, which is epoxide. So that's syn addition. Why does this have to be a syn addition? What do you think geometrically is not possible if this was not a syn addition? Could we have the oxygen, could we have a epoxide form from two different sides? No, that'd be incredibly strained, so that's why it doesn't happen. So that's syn addition here again. Okay, are there any questions on the mechanism for epoxidation? So what's happening here? The oxygen is being both attacked by... Oh, sorry. Maybe I should have... Maybe one of these arrows is... All right, not doing too well on arrows today. Sorry about that. Okay. Boom. All right, we want to do it this way. That attacks that. This attacks this oxygen, and that's why this bond has to break. Sorry, I know it took me 3 times to do that, but see, don't worry about that mechanism. So that's epoxidation. Are any questions on that one? All right, but for epoxidation, what kind of isomers can you get? You can get both the wedged addition, and what else? And the dash, so plus an antimer, okay? All right, thank you. Okay. All right, there's one more for sin. What was that? Does anyone remember the other one? So there's one more. Instead of adding a oxygen, what do we add instead? Carbon, yes. So this is a great way to add to make cyclopropane. So cyclopropanation. Propanation. All right, so this is also sin. Does anyone remember the reagents we use? So let's just use, I don't know, cyclohexane again. All right, to get cyclopropanation, there's two common reagents we use. Diazomethane, and you heat it, or the more safer one, diiodomethane, and a zinc copper couple. So that's just the catalyst, okay? So this mechanism you don't have to know either. All right, but how it works is the zinc copper inserts into the carbon iodine bond, and that forms a reactive intermediate called a carbanoid, and that reacts with the alkene to form a cyclopropane. So what ideally happens here is you get a source of CH2, carbene, like that. Remember, just like with bromine, right, carbenes can also insert. So they insert on the same face of the alkene. So you're going to get insertion here very similarly. Drew that, and that's how we form the cyclopropane. So this is our transition state. Simplified version. All right. So the beauty about this is that the stereochemistry of your alkene substituents, they're the same, they have the same, it's retained. The stereochemistry does not change. So you can form this carbene, this cyclopropane, and all the substituents are in the back. Or what else can you form? What's the other possibility here? Is that it? Just one isomer? No, right? So we get plus what? Plus an enantiomer. Good. So unless specified, just write one enantiomer and say plus enant. Or if I just say draw one enantiomer, just draw one. Okay? Now if you draw both, will I take points off? No. But if it's wrong, yes. So be careful. Okay. So, are we missing any sin addition? I don't think so.
Professor, I have a question.
Yeah, what's up?
So, when we're doing the sin by hydroxylation, the potassium permanganate, what if it's in warm conditions?
Yeah, so if you do it warm, you'll actually get dicarboxylic acid. So that was actually in the homework. So you don't want to do it warm. It has to be cold. You should specify it's cold. And that's the problem with chemistry. Something may be kinetically unstable, meaning it reacts very quickly, even though it gives you a less stable product. All right, so that's all the sin ones. You want to go back here and think about the Markovnikov or anti-Markovnikov? Well, these don't. Cyclopropanation and epoxidation, they don't matter on... they don't add to one side, so there's no Markovnikov or anti-Markovnikov. But what about this one? Well, sin doesn't matter either. But what about this one? Hydroboration oxidation. What kind of regioselectivity is it? So here we should mention that in terms of stereo, it's sin. What about regiochemistry? That Markovnikov or anti? All right, remember, what does Markovnikov say? Which side do we add? If we had an electrophile, we add to which side? Yeah, so the alcohol added to the least substituted side, right? So the regio is anti-Markovnikov. Good. All right. How about hydrogen? Well, hydrogenation, this doesn't matter either. So there's no regiochemistry because they're both the same atom. So stereo, but it's still syn. Okay, so I think we got all the syn ones out of the way. Are any questions on those? So I'll say no to reactions and be able to use them in synthesis, 1, 2, 3 step type synthesis. Okay, not the one we saw in the last exam. No 8 step. Okay, simple 2 to 3, 1 to 3, not 1 step, 2 to 3 at least, 2 to 3 steps at least. Okay, of transformations. And if you go through this packet right here, I do have some synthesis type problems where it asks you to kind of think about what's the best method to do these things. Okay, so please use that as well. All right, so that's epoxidation, cyclopropionation. That's all syn. Got all that out of the way. Now let's talk about anti. All right, which ones are anti-addition? So the common one we saw was this one. BR2 and some nucleophile here. All right. So what happens first here? Do we form a carbocation? Right? No. There's no H. So we can't form a carbocation if there's no H there. So what happens here is our alkene is going to coordinate to this bromine here. And the bromine is going to use one of its lone pairs to attack. And this one's going to attack the bromine, kick off a bromine. And we get something we call the halonium intermediate. So it's basically, it looks like an epoxide, except you have a bromine atom doing some weird chemistry like that. So here, we don't form any carbocations, okay? But we have something that's slightly nucleophilic, like water, like an alcohol or water. Which side does do we attack the or do we attack this intermediate? And remember, this is similar to. Remember, it's very similar to a protonated epoxide. Which side did nucleophiles add if we had a protonated epoxide? The more substituted side, the more crowded position, or the least substituted side? Oh no, think about if we had a neutral nucleophile, not a basic one. Is it the more substituted side or the least substituted side? More substituted. So see this nucleophile, it's neutral, like water or alcohols or acids. They'll attack on the more substituted side because this has a more partially positive side. So this bond right here is partially broken. That's why we attack there. And by which side does it attack? On the same side as the leaving group, the CBr bond, or on the opposite side? So opposite, right? So this is still like SN2 type chemistry. You can't attack on the same side because the bromine is in the way. So we attack right here. And when we do that, what kind of addition is this called? Anti, yes, good. So here, the nucleophile would be right here, and the bromine will be facing in the down position. All right, so here our stereochemistry, anti. What about our regiochemistry? Where is this classified as? Where did the nucleophile add? Markovnikov type addition or anti? So let's call it just Markovnikov. All right, attached to the more substituted side. All right, so you won't see this with acids like HCl, HBr, and that's because they generate carbocation. There's no preference for anti-addition or syn addition because the two groups can add on either face, right? The nucleophile. So here, you're trapped. The bromine is blocking one face, so you're going to add from the opposite side, and that's how we open that. Okay, so when we have this intermediate, it's always going to open on the more substituted side, Markovnikov type selectivity. And the reason why it doesn't work in base is because the base, I think the base would react with bromine. That's why we don't use base. Okay, so the nucleophile has to be weak enough so it doesn't react with bromine. So that's why. All right, so this is called halogenation. So that's our first one for anti-addition, halogenation. All right, so what's a reaction similar to this, but it uses mercury? What do we call that? Oxymercuration, demercuration. All right, so let's do something like this. A little bit different. Okay, so the first reagent is mercury acetate, HgOAc2, and I think there's a solvent. I think it's CHF. All right, if you don't put a solvent, I won't mind. Not for this one. But for SN2 and SN1, you should put the solvent. Okay? All right, so we get this. So the first step, the chemistry is very similar to the halogenation one. What kind of intermediate do we form? No, not carbocation. Well, there's a charged species, but where's the charge on? It's not the carbon, right? Where's it on? Like if this one was on bromine, where will the charge be on this example? The mercury. So you're going to get, let's just draw one isomer. The mercury is going to be bridged here, bridge intermediate, that's what we call them. And then you still have one acetate group right here. All right, so mechanistically speaking, you're responsible for this first step. For the second step, where the mercury comes off, you don't have to worry about that. I taught you the mechanism, but you're not responsible for reproducing that. Okay? So don't worry about that. All right, so then our second step. What was our second step here? It wasn't just water, right? What was it? What else was in there? Oh, wait. The first step has also... What else is in there? Was it It was also water, right? Yeah, we should also have water here in the same step. All right, what does the water do? So usually... unless it's not underneath the arrow, you don't really treat them as solvents. So this water is actually doing something. What side is the water going to attack? Which side? Tertiary side or secondary side? Well, I guess it's only primary side. Yes. Just like the bromine example, more partially positive charge here. So that's why it attacks that position on the mercury. All right, so the mercury now goes back up. And now we've formed our first intermediate. All right, so let's just do it like this. All right, So OH2. And this is a positive charge. So we could just write a proton transfer minus H plus, probably from water. Okay, water is probably going to take that proton. And you can simply just rewrite the product without that extra H. All right. But what happens after this? What happens after that? What's the second step of this reaction? Yeah, demercuration. So I think it's sodium borohydride. Is it sodium hydroxide too? And water. So usually you don't have to worry about reproducing all of that. I would just say the main component is fine. Sodium borohydride. That's the main important part. Okay? And if anything, I might provide you that. So you don't have to memorize all that. Okay? If anything, just put it on your note card. Okay, so then we get, so what does this do? It's called demercuration. So that removes the what? Yeah, the mercury. Good. So now you have just an H here, okay? Now, since this is a radical, remember the mechanism I taught you? It's radical based. So the H and the H and OH are not actually anti-added to each other. It's scrambled. What's was originally the mercury addition, the mercury group, and the OH. But once we remove the mercury, now that's any kind of stereochemistry that was one stereo, it's scrambled. So we lost the stereo selectivity there. So not a good route to take. But again, we can kind of abbreviate here. Stereochemistry is anti. And then what's the regiochemistry? You got murky. Okay, good. All right. All right, there's only two more we haven't gone over. What else is anti? I think that's it. Halogenation and then hydration by oxymercuration. Is there any other anti-additions? I don't think so. All right. So let's list anti-addition. So we already gone over, not anti-addition. We already did anti-addition and syn addition. Now let's do selectivity. Markovnikov, regio selectivity. All right. So we already said 1, oxymercuration. Halogenation. What's the other one? There's some more with carbocations. So we have hydrohalogenation. All right, so R, alkene. So what hydrohalogenation, that sounds like what? Hydrogen and what else? A halogen, so a mineral acid. So HX, HCl / HBr / HI. And we get primarily X, then here another H. That's hydrohalogenation. Now what if we add like something like sulfuric acid and water? What do we get instead? Instead of a halogen there, we're going to get what instead of, if we add water instead? Yeah, hydration, right? So instead we add water, right? H2O, you need a catalyst, H+. And instead of X there, you're going to get OH. All right. So this is a hydration mechanism, okay? So hydration But you can also do those with alcohols. All right. So you can also do so halogenation of X2, ROH. Okay. All of those are not anti. Okay. Some of these are not anti. All of these are Markovnikov Regis selectivity. Okay. So maybe I could bridge it here. Anti, mixed, syn/anti. And why is it mixed here? What's the intermediate? It goes, Drew. What kind of intermediate here? So what happens when I add a hydrogen to the right side of the double bond? What is produced on the left side? What is the carbon now missing? Carbocation. Yep. So this is why here it can go on either face. So that's why I didn't write syn or anti. It's mixed, 50-50 chance. As long as there's it's planar and it has mirror images. All right, that's Markovnikov selectivity. I think I got them all. Am I missing any? No. Okay, good. Thought I missed them for a sec. All right, now what's anti-Markovnikov? All right. What's the first one we saw? The first, I think it's the second reaction we went over. Hydro what? Yeah, hydroboration, oxidation. So hydroboration, oxidation with BH3. All right. Now, you can't actually buy BH3 like that. It's a special chemical. It doesn't actually exist like that. It's a dimer. So BH3 actually exists like this: B2H6 diborane, and you have to heat it to break it up. But that's not important. What's important is that it's not electrophile. That's anti-Markovnikov. All right. Okay. Oh, what if we add HBr, but we don't put it in water? We put it in. We use the gas. And we add peroxides to it. What happened in that situation? HBr, R, OOR. All right. Do you guys remember radical mechanisms? You should be aware of the radical reaction we went over. Radical halogenation of alkanes, cycloalkanes. Predict the products of chlorination and bromination. I even covered it in that packet, so if you want to review, please read that. But this one also does a radical reaction, and it's anti-Markovnikov, right? So let's go over how that works. Just a brief example here. All right, R, like that. So let's do two R's here. R2, R1. Okay, boom, all right. So, HBr in the presence of peroxides and light. All right, what happens first? What's the weakest bond to break in those series of reagents? Is it my alkene? Is it HBr? Or is it the peroxide? Which one is easiest to break? Think about hydrogen peroxide. Why is hydrogen peroxide so unstable? The OO bond is really what? Really weak, easy to break, right? So this bond, what happens first is so we get cleavage there. Remember, homolytic cleavage of the weakest bond, okay? All right. What happens then? What does the radical do now? So RO dot will react with. Okay, so someone refresh my memory. What happened there? HBr, yes. What's the second weakest bond? Not CH, right? HBr. All right. So we somehow have to get Br onto the alkene, so it must be attacking the H. So those are common steps here. You attack the H instead of the Br first. So radical is going to combine here, and we're going to produce ROH, so that gets recycled, plus Br dot. Now what does the Br dot do? No, I don't think so. It's a good guess though. No, not that one. So all the ORs are pretty much broken. If anything, it'll attack another HBr. So now all the ORs, all the ROR, we assume they're all been broken. So they're all been like converted to radicals. So now the only options are HBr and then the alkene. Well, if we attack HBr again, we will just go backwards. So I don't think that's going to happen. So for this reaction to kind of take place, there must be some new kind of bond forming that gives us lesser energy. So that there must be a driving force. So bromine radicals, right? They're more selective. They're selective. So they're going to produce they're going to combine with hydrogen atoms that produce what kind of radicals? More stable or less stable? What's easier to form? Less stable radicals or more stable radicals? More stable. How do we know if something's a more stable radical? It's more what? More substituted. So here we have initiation. Here's propagation. 1, propagation 2. Well, sorry, I don't think that's I think that's part of initiation too. Sorry about that. All right, so Br radical. All right, which side of the alkene does it like to attack? Is it going to attack the left side? So remember, it adds to a double bond. So radicals can also add to a double bond. But which side is it going to preferentially add? The more substituted side or the less substituted side? Less. Dude, remember guys, classify this one as anti-Markovnikov. So if it's anti-Markovnikov, which side must it add? Less, right? And the reason is the intermediate, the radical. So we would prefer a radical go on the more substituted position. It's more stable. So it's because of the intermediate that formed. So here we get this radical. All right, and so now we have R1, R2. Now our radical is very stabilized because of hyperconjugation. And remember, we can attack both from the top face and the bottom face, so you don't get a preference for selectivity. There's no anti or syn addition. And now we have Br here. All right, so that's propagation step 1. What's propagation step 2? Close, not the OR. I don't think it's the OR. No, okay. So let's think about it. So we're going to generate a new radical. So what's the easiest bond to break? Another HBr molecule or ROH? Yeah, HBr. That's the longest bond, right? Good. So this one is going to attack. So for these mechanisms, unless specified, don't write the termination step. You don't have to do that. So HBr right here is going to combine with another HBr molecule. And then this bromine here is going to cycle back up Oops, sorry. And where does this Br go? Which step? Yeah, it goes right back into the chain mechanism. So this is going to be a repeated chain reaction until it all goes away. Like PCR. Polymerase chain reaction. Okay, so that's anti-Markovnikov. Are there any other ones? I think that's it. Those are only two techniques to generate the opposite regional selectivity. All right, so our final product, R1, R2, H. All right. So there's what should I say here? Racemic, no, sin, or anti. All right, but it's anti-Markovnikov. So those are the two options. So now, interestingly, there's other ways to do this selectivity, but we're not going to talk about that. That's a little advanced. Okay. All right, so that's I think that's the gist of it. What other reactions didn't we go over? I think there's only one we didn't go over. You guys remember which one that is? All right, went over hydrogen, went over bromination. We went over, okay. Well, some people said they wanted to go over epoxides again, so let's do that. All right, so one, MCPBA. 2, H3O plus. All right, so for this alkene, what is the product of the very first reaction? Can we pinpoint what kind of functional group that is? So just after the first reaction, let me just, so what's the intermediate here? What kind of functional group? MCPBA, that converted an alkene to what? And? Epoxide. Good. So I'm just going to draw one enantiomer. All right. What does H3O plus do? Outside this transformation right here, fair game. All right. So what does the acid do? It opens the ring. Okay. Well, I made both sides equally substituted. So this is actually going to be a little more messy than I anticipated. So what we get here is protonation at the epoxide, right? And then which side does it open at? But they're both what? They're both as equally substituted. And they're both linear chains, so there's no steric argument. So what happens here is water will attack both sides. So you're going to get openings at both sides of the epoxide. So let's separate this out. So we're going to get one product here. All right. So this is technically dashed, now this is wedged. Oh, but I don't think it matters, does it? Because they're both, well, I think it does, because you're going to get different enantiomers, okay?
So how does this process where it's with one oxygen on the ring, now there's two?
Oh, you mean the ring opening? Yeah, so this should technically be OH2 plus first. Right here. So I showed this one. So let's just do pathway 1 here. So pathway 1 is attacking on this side. So I changed the stereochemistry. That's why it's dashed there. And then on this side, number 2, what's the only difference here? So let's continue with this one. We're going to deprotonate OH OH.
I still don't understand where that alcohol comes
Which one?
from. On that one.
This one?
Yeah, because when you break open the ring, you should have only one alcohol, right?
No, remember there's also the epoxide there. You know, there's this central oxygen right here. See right here?
Yeah.
That one is right here.
Okay.
And then this oxygen is right here.
Okay, got it. Thank you.
You're welcome. All right, but now if we attack on this side, so let's make this the red bond here. So what happens there is we still get substitution. So I'm going to make this a dash bond, OH here. And then this one was also dashed, so we're going to make that wedge now. Okay. So do you notice something about these two structures? How are the final products related to each other? What kind of stereoisomers are they? Yes, they're enantiomers. Okay, so it depends on what side you attack. You get a mixture of enantiomers here. Okay, boom. And I believe it doesn't matter if you attack from the top face or the bottom face, you're going to get the same pair of products. But anyway, you don't have to draw all of them. I will probably ask you just draw one enantiomer, okay? Something like that. So epoxide, still fair game. Open them up with acid, and that's how we get diols. But what kind of diol do we get? What is this called? What kind of diol? Syn diol or trans diol? Trans. Now there are ways to form one enantiomer, but you have to use some special reagent, and we didn't talk about that. So racemic, we get racemic mixture. Okay, so that's alkene reactions, trans diol, syn addition. Okay, what's the last one that we didn't talk about yet? Yes, ozonolysis. All right, so for example, all right, you had 1, ozone, 2, all right, what was it, zinc? I think the most common one I told you, zinc / acetic acid, ACOH. So ACOH is also acetic acid, CH3, CO2H, right? The same thing. All right, so I had an excess of ozone. What happens to all the double bonds? So what does ozonolysis do to double bonds? It just doesn't oxidize them, like we saw with the diol, right? What happens to the CC bond? Anyone? What happens to those CC double bonds? They get converted into what type of double bond now? Oxygen bonds. Oxidize plus double bond formation. Carbonyls. All right. So let's. I like to rewrite it like this. So I put an O on each of the side of the double bond, and then I attach them here. Okay. All right, I just happen to make it symmetrical. You won't always see that. So here I'll put excess. All right, so then you take this compound, just move it apart so you can see what the molecule actually looks like. So this is the same as H double bond O. All right, I don't know if this compound is particularly stable, but it's all right. This could be of theoretical interest. So this is one way you may form this compound, but I've never heard of a tricarbonyl compound that's stable. There's dicarbonyl compounds, but these are probably not stable. But see here, I cleaved all the double bonds, added double bond O. There are originally H's here. H, no H right here, right? No H here. So no H is there, no H. But here, H, H, and H. And we track down all those 4 H's on the molecule. And so that's how you can cleave this molecule. So if you want to reduce the number of carbon atoms in your starting molecule, what kind of reaction should you use? So how many carbons did I start with here? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? How many carbon atoms are in each of these molecules right here? Well, actually, did I have 9? Maybe I don't. Am I missing something? Oh, it's 5, right?
No, there's 10. You miscounted one.
Where?
Between 1 and 2. You missed
Oh, sorry. My bad. So we reduced the number of carbons by what? By half. So you want to go half the carbon atoms, use ozonolysis. All right, that's a technique you can use. Now, is ozonolysis green? No, because you're wasting half of the molecule. But these are the same molecules, so you're actually not wasting anything if you want this target. But it's not symmetrical. You're going to have some waste generated. So mechanism here, do we need to worry about that? What did I tell you guys? No. Mechanism not required. Don't worry about this mechanism, okay? Special ozonolysis, and it's kind of tricky. The reduction step is not too bad, but I would say don't worry about it. All right, I think we went over everything. All right. Halohydrin, don't worry about that. All right, yeah, that's all of it. All right, that's alkenes. All right, we have some time. We want to focus on synthesis. You want to do synthesis? Sure? All right. We can also do some NMR. We have some time. Let's try synthesis though.
Will we ever do alkenes or the NMR stuff?
Oh yeah, potentially. Yes, potentially. So my recommendation for NMR for alkenes is you don't look at the alkene peaks until very last. But there's some patterns you can approach. We can do some before we end today. But yes, if you go over to practice final, I think there are some NMR spectra that feature alkenes, benzene rings, and stuff for that. Okay. Well, we're not going to go over mechanisms for each, but let's try some synthesis. All right. All right. How would you make this? So let's go from here. All right. What happened? Yeah, it's doing like a crip walk here. It just moves to the right side. So how do I move the double bond? Any ideas? Can I just add a nucleophile? Probably not, because that won't react with it, right? Electron repulsion. But what's one way we can get rid of the double bond and then regenerate it using our knowledge of E2 reactions? Oh, that's close. Yeah, I think that would work. Okay. Oh, wait. If we hydrogenate that, what's the problem then? Can we selectively get So the thing is, okay, let's see, maybe. All right, let's go with that. So hydrogenation, what are my reagents then? H2 and yeah, cows. You could have put polyatomic carbon. It's fine. All right. So what's the product that we get here? So what happens to that double bond? Yeah. So you're going to form an alkane instead, right? So write the intermediate product here. All right. Now we have a dilemma. We got rid of all our functional groups, but is there a way we can refunctionalize it again? What's like the only reaction you know that alkanes do? Except, well, don't burn it, because then you're toast, quite literally. So what can we do to kind of make it functionalized again? Ideas? So what other reaction can just alkanes undergo? Radical what? Yes. All right. What halogen do you want to use? Well, I think fluorine's out of the question. Bromine, yes. So we're going to use bromine. Yes, you're right. Tertiary. So, but there's a problem. How many different products can you form? 2. But that might not actually be a problem. So you might get a mixture of these two. My bad. But that might not be a problem, actually. Because what can you do to the mixture of this to get the tetrasubstituted alkene? So how do I go from an alkyl halide to an alkene? Remember, we studied SN2, SN1, E2, E1. What mechanism do we want to promote here? Well, actually, let's think about it. It's tertiary, so E2, E1 wouldn't be out of the question. But, let's see. I don't think it would matter. Okay. Well, just to be safe. So I will actually accept 2 answers. If you kind of, well, we can't just add acid or anything, right? We can't just add water, because what will water do? Instead of bromine there, what will be there instead if we just add water? Will water give you alkene as the major product? No, so you don't want to do SN1. So I think you want to do E2. So what kind of base should we use? You want to use a bulky base or a relatively unhindered base? Close. Think about where the alkene is. Is it on the outside or is it on the inside? Inside. So do we want to use a bulky base? No. So what we know. I taught you guys, right? 2 unhindered bases: sodium or potassium medoxide or edoxide. So use either one of those. Honestly, if you just put NaOR, I will accept that over methanol or something, or ROH. I would accept that. All right. So what you should put is sodium OCH3. Or methanol, over methanol, and I'll give you the product. All right, so see, in synthesis, you can have some kind of creativity here. There's not a one answer fits all argument, okay? But what I was getting at instead was, instead of making it an alkane, I was thinking of making it using HBr. Okay, so what I was thinking was this. HBr. So what would HBr give you here? Oh, sorry, no, aqueous. Concentrated. So sorry, I should be specific. So it'll only be radical, guys, if you put a peroxide source. So just HBr, like a concentrated HBr, it's going to give you Markovnikov selectivity. So where does the Br go in this case? Yeah. Oh, look at here. And then we can go here. And we're done. So we don't run the risk of having a mixture of products. All right, so this structure was serendipitously designed, or it turned out to be that both of these bromides here are in the tertiary position. So they'll produce the same major alkene product when you use a base. So that's some creativity and some things I look for, okay? So I don't just grade off feasibility or, just what I wrote as the right answer. Mine took 2 steps, right? Catherine took an additional step, but that's fine. I think the yield will still be high, okay? All right, so that's a type of alkene reactions where you put 2 types of reactions you've learned. Here, HBr reaction with an alkene, and then we formed an alkyl halide, and then some past knowledge of alkyl halide chemistry to generate the alkene, okay? But my recommendation for synthesis, if you do a lot of practice, so I post a lot of practice from that packet I gave you, not this one, but the other one, like around a few weeks ago, before the 3rd exam. I think there's some synthesis there that could help you, all right? All right, so this is like an example of an alkene type synthesis problem. Do we want to do one more, or do we want to go over to NMR? All right, let's do one more. Not from the new stuff, okay, but from the old stuff. All right, so let's say we have all right. I want to take my alcohol and convert it to an ester, but the ester has the same stereochemistry as my alcohol. How do I do that? All right, so you guys, if you think do NABR and then sodium acetate, that won't work because that's an alcohol. You have to convert to a good leaving group first. All right, so how can we get retention of stereochemistry? Well, we can do 2. What kind of reactions? No, not SN1E1. Take the other one. SN2. If we do 2 SN2s, right, we invert it first, then invert it right back. We get the same stereochemistry. Oh, okay. So we convert this. Let's do some retrosynthetic analysis. Let's cut this bond. So that looks like we can have something like this, right? X plus sodium OAC. So this is OAC. AC is this group. The acyl group. All right. What kind of solvent should we put here, though, for this reaction? You want a proic solvent or aprotic solvent, if it's SN2. Aprotic. That's our favorite one. I think our favorite one, DMSO. Or acetone, or DMF, whatever you want. Don't do water. Okay, so how can I get from X to OH here? I need to convert OH to a good what? Leaving group. Good. All right. So I need something like this. All right, so actually, let's just go backwards. Let's just do it from here. All right. So, what's one way we can convert directly OH to a good leaving group? We learned some methods, right? If you use an acid, I don't think it will matter because, well, actually it does. Because what happens if you use acid? Are you going to get just a single enantiomer? No, right? Secondary is like in the midway between SN1 and SN2, so you're going to get carbocation intermediate, so you don't want that. So, but what's the way we can avoid carbocations? Oh no, that's acid still. Yeah, no acid. So what's one of those reagents where we avoided carbocation formation, but we were still able to do SN2 type chemistry? They had like sulfur in them and like phosphorus. Do we remember one of those? On the last exam, you could have done that for one of the synthesis boxes. Like instead of HBr, you could have picked phosphorus tribromide. So PBr3. So if you react PBr3 with the alcohol, you'll get this as the bromide. And then you can do another SN2 type reaction to get the acetate. So those are like the kind of synthesis problems I put. Something related to SN2, E2, and then one for alkene. And if you've been looking at the practical exams, I usually kind of sort of mimic what I put on there, like just like a much more simple one with ethers. So usually an alcohol, you usually Grignard, maybe a Grignard one, using Grignard reagent, like we saw in exam 3. SN2 type chemistry, and then the last one is some alkene type chemistry like we did here. All right, so you saw an alcohol one, so here's the second example. You saw the alkene one, that was the first example. And then the third one you can expect is something with maybe a Grignard, or ether type chemistry, ether chemistry. And if you look in that packet, that review study guide I gave you, it covers both type of syntheses using these two types of reagents. Okay? All right. So in terms of old material, stereochemistry, you don't need to know percent EE, but you should be able to tell me, if I gave you a structure, can I predict its optical activity? So you can't forget that stuff, okay? Don't forget about drawing. Don't forget about resonance. In terms of resonance, probably not going to focus too much on you drawing resonance structures, so you don't have to worry about that. I'll just tell you that. All right. All right, we have some time for some other stuff. I think I heard from some of you, NMR. Does that sound like a good idea? Okay. Which one do I want to do? All right, so I'm going to project some NMR problems, okay? Let's do a few examples. There's a few examples. So you went on the NMR DB website I kind of posted. It's pretty cool, but let me just pull up a problem here. All right, here we go. All right. All right, which one did I do? Okay, so exercises, structure elucidation. All right, which example did I pull up? I don't want to give you the structure. C8H10. All right, can you guys see that? I guess not too well. Let's just exit. All right, CHH10. How do you go about doing this problem first? What should you calculate? The degrees of saturation. All right, let's start by doing that. So what's the degrees of saturation? I can't write on this browser thing, so I'm just going to write on the board. All right, C8H10. Once you got the degree of saturation, why don't you share that if you want? You guys, if you want to go on this website, it's great to practice NMR. It's called NMR Database DB, nmrdb.org. All right, did anyone get the degrees? 4, all right. If you have 4, what does that scream out? What kind of functional group? Yeah, but remember when I said it was exactly 4? What kind of ring do you think it could be? Not just any ring. Starts with a B. Benzene. And how do we know it's a benzene? What is in the 7 to 8 region right there? We have about, okay, I know you can't see that. That says 3 plus 2, and that's 5. So that's a benzene ring, right? So degrees of saturation 4, you're going to automatically think benzene ring. All right, so that means that that signal is for 5 hydrogens. You don't have to worry about the splitting because how is this substituted then? If there's 5 hydrogens still, how many attachments are there? 2, 1. Well, if there was 2 different attachments, how many hydrogens would be present? 4, right? So if there's 5, how many attachments are there? Only 1. So we have something attached right here. So that takes care of our 5 H's at 7 to 8 ppm, right? All right. This is the level you can expect, okay? You also get IR, but I don't think IR will help you here. All right, all right, so these other 2 peaks here, you see there's one at 2 hydrogens at about 2 ppm. And then there's 3 of them, and I'll tell you right now, it's a quartet for the 2 hydrogens and a triplet for the 3 hydrogens. If we think about that, what kind of splitting pattern gives you this? Quartet for 2H and 3H, you get a triplet. What kind of fragment is that? That's 5 hydrogens. You get a quartet and a triplet. It's an alpha group. You piece the molecule together. This is ethylbenzene. All right. So you don't have to worry about mass spec. I won't provide any of that. You'll get the formula. That's all you need, and IR. Okay. And there's also some practice problems for IR in that handout. So if you want some additional practice with deciphering IR, please use that. Okay? And notice here that you can notice right here that you see these splitting patterns in here for the benzenes. They're very complex. They're like quartet of doublets. And remember those complex splittings? I told you guys you don't have to really know them to decipher a structure like this. Okay? So you always think about some shortcuts you can take. All right, so that's a benzene example. Maybe you can expect a benzene example. What about alkene? We talk about alkenes a lot. So maybe let's try an alkene example. I can find a good one. Let's see. Okay. All right. Is everyone okay with that analysis? Any questions? So does anyone want me to explain again the procedure there? So I'll say this. On the final, make sure you have a strategy. Okay, don't get bogged down in a question you can't solve. Try to aim for most points as you can get. And especially OChem, like this late in the semester, it's supposed the learning curve is supposed to kind of skyrocket to like 3 levels above. It's normal. Okay, I've seen it every time. So just give you some advice. Okay, but let's do one more NMR. I'm going to do an alkene example this time. Okay, so I'm going to bring up. Let's check our answers here. So this was structure 3, and we were right. It's ethylbenzene right there. See that? We were right. There we go. So I would not toggle the answers until you attempt it. Okay. So now let's do this one. We're going to do number 16. This one right here. All right. So I think we can see the peaks here. All right. At 6 ppm, that's a doublet. Okay. At 5.5, that looks like a, I would say like a 6-member peak, I think. Yeah, I think that's a very complex peak, and it's only one H, so don't worry about that one yet. The one at 4 ppm, you probably can't see it, but I think that's a quartet. Number 4, that's a quartet. Okay. What about here at number 2? We have 2 peaks that for 3 hydrogens each. One looks like a doublet, and one looks like a triplet. You don't have to you don't have to be able to decipher them. I will give you a hand and tell you what the splitting pattern is, but you have to know what the one-letter abbreviations mean. I won't tell you what an S means, what a quartet means, a Q, a T, or a D, or if it's really big, like 6 peaks, 7 peaks, 8 peaks, I will only tell you it's a multiplet, lowercase m. All right, so do we have an idea? Okay. Well, we notice here at the 5 to 6 region, that usually indicates what kind of functional group. Don't worry, you'll get the NMR chart. Do you remember? All right. So at 4 to 6, alkene hydrogens. So it looks like we have an alkene hydrogen. And don't worry, you'll get IR too. So I didn't show you IR, but you'll get IR too. All right. But first, let's calculate degrees of saturation. Did anyone calculate that? One, okay. So we have C5, H10. Oh, so that's 1 degree of saturation. So that should be what? Right away, we could probably guess it's a double bond alkene. So we have something like that. Okay. So look at our alkene peak. From 4 to 6, how many hydrogens do we have there? So we have 1 at the 6 ppm, and then how many hydrogens is for the 1 at 5? It's 1. Okay. All right. So I must suggest something. We didn't learn coupling constants for alkenes yet. I'll talk about that next semester. Okay. But you may be wondering, okay, if there's only 2 hydrogens, is it the cis isomer or the trans isomer? So with the information I provide you, you can't pick one or the other. So either would work. But in this case, you have coupling constants. You won't get that on the exam. Okay? So you don't have to worry about that. If the coupling constant is like from 412 to 18 hertz, which it is right here, see that 13.8? Well, I didn't mean to do that. Okay. When it's like 12 to 18, that's a trans alkene. So right away we know it's a trans alkene. So we can write the H in the trans position. All right. Now the question is putting everything else together. Okay. So what's this peak at 4? That's going to be relatively close to what kind of element? Oxygen. Good. All right. How many hydrogens do we see there? 2. So maybe we can put it like, okay, what if it's like, now the question is, where is the hydrogen? Or sorry, where is the oxygen? Okay. Well, look at the peak at 4. How many neighbors does it see?
2 neighbors.
2 neighbors, right? Oh, if I put it here, if it's next to an alkene, that splitting won't be so nice. It won't be so clean. So we can eliminate this possibility. It's only 1 neighbor, right? Look at that, 1 neighbor, doublet. I believe that's it. So let's put the oxygen here instead. So there's no neighbors. All right. So there's 2 hydrogens there, right? So we said it must be directly attached to the oxygen. Okay. But we need to see how many neighbors though. Oh wait, did I say it's a quartet or a triplet? All right. Oh, okay. Upon further inspection, I didn't get to say what? Quartet. So how many neighbors must this one see? 3. So let's put what kind of group at the end here? Methyl, yes. Because look, 1CH3 is what kind of splitting here? The one first upfield is a triplet, right? So that would make sense. That's a triplet. Okay. Now all we're missing is this other 3H here. Okay. So where does that have to be? On the other side. And look at this tall peak. It looks like a doublet. I will tell you if it's a doublet or not. So if I put a methyl group here, how many hydrogens does it see? Only sees 1, right? Only sees this one. So that methyl here can be a doublet. Doublet. Here, multiplet. This 1H doublet. Then here, quartet. And lastly, triplet. Okay. And if there's no other questions, we're out of time. Well, I'll still hold office hours. Come by tomorrow, Wednesday, Thursday, also Monday if you're here. If not, good luck with studying, okay? Remember, guys, exam 12 p.m. on Tuesday, December 9th. And guys, if you want your old cheat sheets, I have them here, but you don't have to take them if you don't want it. Huh? Yeah, sure. All right, anyone I get a final review packet? Very helpful to review for the final. Yeah, which one is it? Which one is it?
I can't recognize my name.
Alright. Are we all caught up with everything around them? Good? No, just review for final. Go ahead, yeah. Okay. Are you sure? Okay.